Okay, so in this video, the plan was to run through an example calculation of each of the objectives for this week. So this week there are a total of 10 objectives that you need to complete, and you need to get 3 questions in a row correct of each topic. So I had a few questions from folks about where I got my calculator emulator from that I use. I use it both on my phone and also on my computer, and the emulator that I use is called Wabbit EMU, and I posted information in the week 2 module for this week in the resources section. It says scientific calculator emulator. So to get this to work on both your phone or on a PC, you will need 2 files. You need the emulator itself, and then you also need a ROM, which is basically the file that gives the description of the calculator. So I put both of these up in the module, so you can just download both these files, run the emulator, and it'll prompt you for the ROM. Now, if you want to, this is for PC that I put here. If you want to get it for your Android device, you can get that through the Google Play Store. Again, you'll need to get a ROM, and you can get the ROMs from this final link here. Apparently you can also run this on Mac or Linux. I haven't tried this, but I got information from the Wabbit website that said that those files are available on GitHub if you want to get them. So if you have trouble with that, just let me know and I can show you how to set it all up. It's really, really easy. Okay, back to the problems though. So this first problem here is all about using a rate law. So just in case you don't know, a rate law is going to look like this. Rate equals a constant K called the rate constant multiplied by the concentration of each of our reactants raised to a particular power. And these powers here that I've indicated with the lowercase letters, they're called the order of that reactant. And if you add all of the powers together, 3 of them in this case, you get the overall order of the reaction. All right. So and those numbers can be 0, 1, 2, 3. They can be they can actually even be negative numbers, but they're normally a either 0 or a positive integer in the examples that we're going to be looking at. So you get one of these terms for each of your reactants. Okay, there we go. So that would be the rate law for that expression. Now, what does the rate law tell you? The rate law tells you how sensitive the rate is to the concentration of each reactant. So for example, if it is 0 order, you know that A to the 0 is just the same as 1. It doesn't mean that, it means that the concentration of A doesn't affect the rate of the reaction at all. If it is second order, it means that every time you change the concentration of your reactant by some factor x, the rate will increase by x squared, right? And if it is first order, it means if you change the concentration of C, or let's call it something more interesting than first order, that's kind of boring. Let's say it's like 5th order. If you change the concentration of C by x, then the rate will change by the factor of x to the 5. Okay, so basically, the bigger the reaction order, the more sensitive the rate of the reaction is to changes in the concentration of that particular reactant. All right, so in this case, we're given the rate law, and it says that it is 3rd order in N2 and 1st order in O3, all right? So we don't normally put the 1 in, right? Because O3 to the 1 is exactly the same as the concentration of O3. So we don't normally put the 1 in just because it's kind of redundant. Okay, so 3rd order in N2 and 1st order in O3, 4th order overall. So the reaction order in N2, it is 3rd. The reaction order in O3, it is 1st. The overall reaction order, 3 plus 1, it is 4th order. So that's pretty simple stuff, right? Just understanding what we mean by that terminology. And then it says at a certain concentration of N2 and O3, the initial rate of the reaction is 0.19. So rate equals 0.19. And then it says, what would the initial rate of the reaction be if the concentration of N2 were doubled? So I'm going to change the concentration of N2 by a factor of 2, which according to my rate law means that the rate has to be multiplied by 2 because it's third order in N2 to the 3. You see how that works? So that's what I've got to do here. Rate is going to be 0.19 times 2 to the 3. I doubled my concentration of N2, so my rate is going to get multiplied by 2 to the 3 to reflect that. Okay, so what do we get? We want this in 3 significant figures, 0.19 times by 2 to the 3 or by 8, all right? 0.19 times 2 to the 3. Enter. 1.52, and then the units are already given, so we don't have to worry about that. And that's going to be 3 sig figs. 1.52 molarity per second is our new rate. Okay, so we got that guy done, 1.52, and it went up. And that makes sense. You tripled the concentration, you doubled the concentration of N2, and the rate went up, as it should do. Okay. What about the next one? The rate of the reaction is measured to be 29. So rate equals 29 molarity per second. When N2 equals 1.2, so the concentration of N2 equals 1.2 molarity, and the concentration of O3 equals 0.11 molarity. It says calculate the value of the rate constant to 2 significant figures, and thankfully they gave you the units, so we don't have to look them up. So that's cool. So what do we know? Rate equals K N2 to the 3 times by the concentration of O3. So then K is just simply rate divided by the concentration of N2 cubed multiplied by the concentration of O3. So we just got to put all of our numbers in, right? So it is 29 divided by parentheses 1.2 cubed times 0.11. And that'll be our K. And we have to give this to 2 significant figures, and we don't have to worry about the units because the units were already given for us. So 29 divide parentheses 1.2 to the power 3 times 0.11, close parentheses, enter. And so to 2 significant figures, this is going to be 150, right? Now, there's a little bit of a difficulty here writing this to 2 significant figures. 150, I just got to remember, don't put a decimal point on the end because that'll be 3 significant figures, because then the trailing 0 will count, right? Now, there is another way around this, and that would be to put it into scientific notation. If you put it into scientific notation, eventually, then you'll see that it's another way around it of making it clear that you only want 2 significant figures would be 1.5 by 10 to the 2. So either or, you can either write 150 without the dot on the end, or you can write 1.5 by 10 to the 2. And then the units, like I said, are given, so you don't have to fuss with that. So in this problem, what you're given is a written description of a rate law, and then you're given some data and you have to calculate a couple of rates. So let's read the description of the reaction. It says, a certain reaction is second order in N2 and first order in H2. So what that means is that the rate is equal to the rate constant multiplied by the concentration of N2 squared multiplied by the concentration of H2, and we don't have to write that it's to the power of 1. And what this is really saying is that the reaction is more sensitive to changes in the concentration of N2 than it is in H2. So for example, if the concentration of N2 changes by a factor X, the rate will change by the factor X squared. But for H2, if the concentration of H2 changes by X, the rate will only change by a factor of X to the 1, or just straight up X. So you can see it's going to be more sensitive to changes in concentration of N2 than it is to changes in concentration of H2. All right, so let's look at the problem. So in the first line, we're given concentration data and the rate of the reaction. And this is just kind of code for telling you what K is, because K is just the rate of the reaction divided by N2 squared multiplied by H2. So the first line is really just allowing you to calculate what K is. And then once we've got K, because we've got the rate law, we can figure out the rate as long as we have concentration data. So we've got 16 divided by 1.25 squared times 2.22. And we don't have to worry about thinking about what the units for K are if we don't want to. I know what they're going to be. They're going to be molarity to the minus 2, seconds to the minus 1. Because we're just using this for our intermediate calculation, and just quickly doing this, that's going to be, I think, 4.6 thereabouts. So 16 divided by 1.25 squared. I should have put my parentheses in there. And then I'm just going to divide that by 2.22. There we go. So 4.613. Now, I'll show you, I did that kind of in a lazy kind of way. It should have been 16 divide parentheses 1.25 squared times 2.22 close parentheses 4.613. There we go. All right, so 4.613. There's my K. All right, so we've got K, so now we can just go on and calculate anything, any rate where we have the concentrations, right? So rate equals K N2 squared H2. So we got K is 4.613. And in this second case here, the concentration of N2 is 5.66 squared, and the concentration of H2 is 2.22. So what we're expecting is that it's going to be a lot quicker than 16 because the N2 went up quite a bit and the H2 stayed the same. So it's going to be quite a lot quicker. So let's see what we get for the rate when we put all of that into our calculator. So we want 4.613 times 5.66 squared times 2.22, and we're going to go 3 significant figures. So it is 328, and the units are molarity per second. So 328 molarity per second. And that makes sense, right? We increased the concentration of one reactant a lot by about a factor of 4.25, and then the rate should have gone up quite a bit. In fact, it should have gone up by about 4.25 squared. So that makes sense to me that it went up like that. All right, now we've got to do the same thing, but for the information that's in the final row. Now, a little bit more complicated here. Because when you look at the data here, what you see is that the concentration of H2 also goes up relative to experiment 1. It goes up by about a factor of 4. But the concentration of N2 changes by about a quarter. So one goes down, one goes up. So you would expect that these effects could cancel one another out. The change in the concentration of N2 is going to slow things down, but the change in H2 is going to speed things up. But remember, it's more sensitive to changes in N2, so the slowing down is going to win out. So I'm expecting that my rate is going to be less than 16. Let's see what we get. So my K, 4.613, my N2, 0.313 squared. I should have written it on that line, shouldn't I? And then my H2, 8.86. There we go. So K, N2 squared, H2. And I was betting that it was going to be less than 16. Let's see what we get. So 4.613 times 0.313 squared times 8.86. Let's see what happens. Oh, it quartered. 4.00 moles per liter per second. Now, why is that? Well, the concentration of the N2 got multiplied by a quarter, so that will make the rate get multiplied by a quarter squared, but the concentration of the hydrogen got multiplied by 4. So another way of writing this would be 1/4 squared multiplied by 4. So that will go. So we would expect the rate to get quartered. And sure enough, what's a quarter of 16? It's 4. So it all makes kind of logical sense once you understand that the order is just really kind of the sensitivity to the change in concentration. All right, we've got 2 of these guys done. Let's see if we can get this third one done. More initial rate stuff, okay. Some measurements of the initial rate of a certain reaction are given in the table below, okay. So in the first 2 experiments, it looks like the concentration of N2 there, it basically doubles, but the concentration of H2 stays the same. So I'm going to be using experiment 1 and 2 to figure out how the rate depends on the concentration of N2, okay? And then in experiments 1 and 3, what I can see is that the concentration of N2 stays the same, but the concentration of H2 increases. So I'm going to use experiments 1 and 3, I should draw that in properly, 1 and 3, to figure out the dependence of the reaction rate on H2. So the rate law is going to be like this, because we have those 2 reactants, right? And what I have to do is figure out what A is using data from experiments 1 and 2, because that's where we're varying N2 while keeping H2 the same. And then I have to also figure out what B is. So how do I do this? Well, I use the log rules, don't I? So it's going to be a log of rate 1 on rate 2 divided by log of the concentration of N2 in 1 over the concentration of N2 in 2. Now, can I eyeball it? Yeah. This here went up by about 2, and the rate here, when I go from across there, it goes up by about 2. But the rate here goes up by about 2 squared. So it goes up by about a factor of 4. So I'm guessing this is going to be second order. We'll see what we get. we'll see what we get. So it is going to be log of 2 by 10 to the 5 on 8.31 by 10 to the 5 divided by log of 1.57 divided by 3.20. And like I said, I'm guessing it's going to be second order. Let's see what we get. Log 2 by 10 to the 5 divided by 8.31 by 10 to the 5. I guess I didn't have to put in the by 10 to the 5 if I didn't want to. Divided by log 1.57 divide 3.2 close parentheses. Come on, 2. I knew it was going to be 2, didn't I? I told you it was going to be 2. So it is second order in N2. Right, now we're going to look at experiments 1 and 3 and figure out the order of H2. So let's see if we can eyeball it, right? So between experiments 1 and 3, this guy went up by, I don't know, like, 1.5. Went up by about 1.5, but the rate also went up by about 1.5, right? Because 2 times 1.5 would give me 3.5. So I'm guessing, just eyeballing it, that it is first order in H2, but that's not good enough. Right? We can't just eyeball stuff like that. It's going to be not cool. So log of rate 1 over rate 3 this time, divided by log of the concentration of H2 in 1 over the concentration of H2 in 3. That's what's going to give me B. So get my numbers in. So log of 2 by 10 to the 5 over 3.58 by 10 to the 5 divided by log of, what do you got there? 0.43 on 0.770. And like I said, my wild stab in the bark is that it's going to be first order. I'm always happy to be surprised though. It's so easy to do the math. You don't want to eyeball it. It's just kind of a double check, right? Just a double check to make sure that you didn't get anything weird going on, because weird stuff happens all the time. Let's see what we get. Oh, so close to 1. So it's first order in H2. All right, so now we've got both the orders. We can answer that first question, which is, what is the rate law, right? And the rate law is that it is second order in N2 and first order in H2. So what we want to do now is we're going to reorganize the rate law and we're going to solve for K. So rate equals K N2 squared H2. So that means that the rate divided by N2 squared multiplied by H2 will equal K. So I always pick the data for the first example. All right, so in the first example, here's my numbers there. So it was 2 by 10 to the 5 was my rate. My concentration of N2, I'm always really careful at 1.57. That has to be squared. And then my concentration of H2, 0.43. All right. There we go. And let's see what we get. All right. 2.0 by 10 to the 5 divide parentheses 1.57 squared times 0.43, all closed. There we go. And I think it could be good to have this in scientific notation. So mode over enter second function quit second function answer enter. There we go. And to 3 significant figures, which is consistent with what our concentrations were, this would be 1.89 by 10 to the 5. There we go. Now I do need to figure out, oh, perhaps I don't. No, I do need to figure out the units here. So it's always going to be whatever my concentration units are, raised to the power of negative of the overall order minus 1 multiplied by time to the minus 1. Now in my case, the overall order 2 plus 1 is 3. So it's going to be concentration to the minus 3 time to the minus 1. And then I just have to look and see what my concentration and time terms are. That is wrong. Overall order minus 1 is 3 minus 1, so it's concentration to the minus 2. So, all right. So now I've just got to look for what my concentration were. It was molarity, and then my time was seconds. But I always want to double check that. Molarity and seconds. So it's going to be molarity to the minus 2, seconds to the minus 1. Right? That's going to be my units. Molarity to the minus 2, seconds to the minus 1. It's pretty easy once you get a grip on the units for rate constants. Okay, I feel happy about that. So let's move on to the next one. Okay. So what we're going to do here is we're going to calculate the change in concentration after a whole number of half-lives of a first order reaction. So the half-life of a first order reaction is given by this. It is log 2 on the rate constant. Now, the thing about the half-life of a first order reaction is you can see that it doesn't depend on the concentration of anything, right? It is a fixed amount. So what that means is if I start with 100% of something, 100%, and then here I've got 50%, and then say down here I've got 25, and so on. The amount of time that it takes it to halve it every time, and say 10 seconds, right? It's the same. It doesn't change, right? So if I want to go to 12.5%, you guessed it, it's going to take another 10 seconds. So the half-life is a constant. Right. It also means if we have the half-life, we can get the rate constant really easily. Okay, so that kind of really helps us out. So this reaction here is a first order reaction. So we also know something else about the reaction. We know that rate is equal to K times the concentration of our reactant to the power of 1, or it's just first order. All right, and in this case what we've got is our drug is just kind of getting eliminated out of our body. There's only one reactant. Okay, so this is going to be my strategy. I'm going to take my half-life, I'm going to turn it to K, and then once I've got K, you guessed it, I can use my rate law to get whatever I want. Okay, so that's important. There's another thing about first order reactions that have only one reactant is we can use what we call the integrated rate law, and that says that the log of our concentration at some time t is equal to the log of our original concentration minus kt. So that can be really helpful as well. Okay, so we've got a couple of ways of solving whatever problem that we might be posed. because once we've got K, not only can we use the regular form of the rate law, we can also use the integrated form of the rate law. So let's see what they're going to ask. The rate at which a certain drug is eliminated from the body follows first order kinetics, okay, with a half-life of 86 minutes. Suppose in a particular patient, the concentration of this drug in the bloodstream immediately after injection, so this would be T equals 0, is 1.8 micrograms per milliliter. So I'm going to call that is my original concentration at T equals 0. What will be the concentration 172 minutes later? So I've got a plan here. I'm going to take the half-life, I'm going to turn it into K, and then what I'm going to do is I'm actually going to use this form of the rate law, the integrated rate law for a first order reaction, along with my K, my T, and my initial concentration to calculate the logarithm of the concentration at time T. So that's going to be my general strategy. So K is equal to log 2 on T a half. So T a half in this case was 86 minutes, right? So I'm just going to work in minutes for this. Log 2 on 86 minutes. And so K, you can see, will have units of minutes to the minus 1. So turn my calculator on. Log 2 divide 86. And then that gives me my K, right? 8.060 by 10 to the minus 3. Okay, so now what I'm going to do is use my integrated rate law for a first order process. Log of A at times T will equal to log of my original concentration minus KT. And I have all of this information. My original concentration was given in micrograms per liter, right? There it was 1.8 micrograms per milliliter. So this equals log of 1.8. And then my K, which I just calculated, 8.060 by 10 to the minus 3. And then my time was like 172 minutes. There we go. 172 times 172. All right, so that's it. So the log of A at times T. Now log values don't have any units, by the way. So log of 1.8 minus my answer from before, which was my K, times by my T, which was 176. So that equals negative 8.3075 times 10 to the minus 1. So then my concentration is just going to be E to the minus 8.3075 by 10 to the minus 1. So I'm just going to go second function, natural logarithm, second function, answer to bring up the answer that I had before, and then enter. And there it is. It is 0.436, right? So concentration of A at that time of 176 seconds is going to be, this is in scientific notation, 0.3572, and that was micro, what was it? We should check. We shouldn't make assumptions here. It's micrograms per milliliter, all right? Micrograms per milliliter. Okay, so we want the correct number of significant figures, so it's going to end up being 2 significant figures, so it'll be 0.44 micrograms per milliliter. 0.44 micrograms per milliliter. So 1.8. Right, so let's just kind of say like 86 minutes is 1 half-life. So if we go from 0 to 86 minutes, the concentration should become 0.9. If we add another 86 to that, where do we end up? 86 plus 86, we go another half-life. Who'd have thunk it? We've gone 172. Right? So it should halve again and be 0.45. And that's exactly what we discovered. Alright? There we go. There. But we did it exact, didn't we? Alright? So basically went for 2 half-lives and it halved and then halved again. Alright? Does it make sense? We halved it and then we halved it again. Oh, the reason why I'm slightly out, I don't know why, I did 176 instead of 172. There we go. I just picked that up. And so if we reevaluated that, it would be slightly different. So log of 1.8 minus 8.06 by 10 to the minus 3 times 172. We go, and then second function, second function, answer. There we go, and we got our 0.45. Okay, to 2 sig figs, that's 0.45 micrograms per milliliter. So it was 2 half-lives, so it should have halved twice. Now, being able to do it properly or being able to do it completely the way that I showed, going through the integrative rate law, is important. You can't just always depend on being able to do it by examining the half-lives, okay? You need to be able to do the math. Okay, using a zero-order integrated rate law. So zero-order integrated rate law is this guy. This is the concentration at time t is equal to the concentration originally minus kT. Now, there is an interesting table in your book. Let's just find it here. This guy here, we'll just grab it now. And it has all of the relationships between the integrated rate laws and the half-lives. And I'll show you something cool about it. All right, so here it is, 12.2. For a zero-order reaction, what you can see is that the half-life will increase as your concentration increases. Or we could also say that the half-life will decrease as the concentration decreases. So in a chemical reaction, the concentration of reactants decreases as time goes on. So what did we say? We said that the half-life will decrease as the concentration of the reactants goes on. So the half-life gets shorter and shorter. So to get to, like, say 50% might take 10 seconds. But because the half-life gets shorter, to get to 25% might only take, say, another like 7 seconds. And then to get to 12.5% might take only like another 5 seconds, right? So the half-life keeps getting shorter and shorter and shorter as the reaction progresses, which is interesting, okay, for a zero-order process. Now, for a first-order process, we saw that the half-life is not affected by concentration. I don't know why my pen is being weird. There we go. My half-life is not affected by the concentration. So half-life is a constant. But for second order, we got a weird relationship here that shows that the half-life is dependent on the concentration of your reactant, And in particular, that as the concentration of your reactant gets smaller, your half-life gets bigger. So for second order, as your concentration decreases, your half-life gets longer. So there's 100%. After one half-life, you'll be at 50%. So maybe that takes 10 seconds. And then after two half-lives, you'll be at 25%. But maybe that takes like 12 seconds because the half-life is getting longer. And then after three half-lives, you're going to be at 12.5%. And maybe that takes like 15 seconds. So your half-life just keeps getting bigger and bigger and bigger. And that can be really helpful. If you can observe that the half-life is getting bigger or smaller, you can tell sometimes what the order of the reaction is, or at least get a loose feeling for it. So here it is for, there's the integrative rate law for zero order. Okay, so let's see what we've got. It says, under certain conditions, the rate of this reaction is zero order in ammonia. So rate equals just K. Or we can say that the concentration of ammonia at time t is equal to our original concentration of ammonia minus KT. Now in this case, we're given the rate constant. It says with a rate constant of 0.0053. So K equals 0.0053. Now if I wanted to, I could calculate T a half. You see that? Because I got the formula there for it. Right? After how much time is there only 50 millimoles left? So we're going to, read this again. Suppose a 4-litre flask is charged under these conditions with 100 millimole. After how much time is there only 50 millimole left? So what are they giving me? They're giving me the original concentration. They're giving me K. They're giving me the concentration at time t, and they're asking me to solve for t. So I've got to reorganize this guy to solve for t. So that's what this is all about, right? I've got to solve for how long it's going to take to get to that concentration. So let's reorganize this expression here. The concentration of ammonia at time t, and then the first thing I'm going to do is I'm going to subtract the original concentration of ammonia. Then, if I divide that by minus K, I'll get T. And so that's it. So my original concentration of ammonia was 100. My final concentration was 50. And then my K was 0.0053. And that'll give me my time. All right, that'll give me my time. All right, so let's do that. So 100, sorry, I got to hang on a second. Let's repair this. The concentration at time t, I kind of did a little switcheroo in my head, is 50. The original concentration is 100, and we need a minus there. I just kind of did that little cheeky shorthand. So 50 minus 100 is my top row. Divide minus 0.0053. Hit enter. There we go. 9,434 seconds. Right? 9,434 seconds to the nearest whole second. Okay, so to go from 100 down to 50 is to halve the amount. So this number here is really just the same as the half-life. So if I wanted to, I could have calculated it using the half-life formula, but I don't think it's really any easier than using the integrated rate law, because the half-life formula and the integrated rate law are exactly the same thing. One is derived from the other. But if you wanted to, you could have calculated the half-life, and that would be the same number. I'm not going to go through doing that math now, okay? All right. Okay, let's move on to the next objective. Using an integrated rate law for a first order reaction. So I'm going to get my table of integrated rate law stuff, and it is that stuff in there that I'm interested in. Okay, so we've got the rate constant, there it is. So we know that rate equals K, and this is first order in the reactant, so it's going to be like that. And we also know that the integrated rate law applies. So the log of the for a first order process, the log of phosphoric acid at time t is equal to the log of the phosphoric acid originally minus Kt, and we also know that T1/2 is equal to log 2 on K. So that's kind of like all of the key relationships that we might need in here. So it says, suppose a vessel contains phosphoric acid at a concentration of 0.63 molar. So that's my original starting concentration, right? 0.63. Calculate the concentration of H3PO4 in the vessel 23 seconds later. So that's my T. And then in the first part of the problem, they gave me my K. So I've got that 0.0502. So this is just going to be plug and chug, isn't it? All right. I'm just going to use my formula there for this. So that's not going to be too hard. So the log of the phosphoric acid concentration at time t is going to be equal to my log of my original phosphoric acid concentration, which is 0.63, minus my K, 0.0502, times by my time, which is 23. So the log of the H3PO4 at that time of 23 seconds will be ln 0.63 minus 0.0502 times 23. There we go. So minus 1.6164. Now, we don't want the natural logarithm of the phosphoric acid concentration. We want the actual phosphoric acid concentration itself at that time. And so that's going to be e to the minus 1.61664. Now, what do we know? The phosphoric acid is a reactant. So when the reaction has been allowed to run for 23 seconds, the concentration should be lower than what we started with. So we started with 0.63. So whatever I get for this guy, it should be less than 0.63. If it's a bigger number, I know I got something wrong. So I'm going to go second function, E, and then I want to bring the answer back from my previous calculation and then enter. And it ends up being 0.199 to 3 significant figures, right? 0.199. And we'll figure out all the units and the sig figs now. So how does that end up being? So the units are going to be molarity, and we need to give our answer to 2 significant figures. So 0.199 to 2 significant figures would be 0.20 and then molarity. And that makes sense because it's a smaller amount than 0.63, right? So that's cool. So I'm happy with that one. Okay, so in objective 7, it looks like we're going to use the second order integrated rate law. So going to my table, 12.2 from the book, second order, and there it is there. And there's a few things that we know. So the rate law is going to be our rate constant times by the concentration of our reactant, which is this guy here. I'm not going to write that whole thing out. I'll just call that A, and it's second order. Okay, and they give you a whole bunch of stuff. They tell you what K is, so we've got that guy. That's cool. And then because it's second order, we know that the integrated rate law will have this form. 1 on the concentration of our reactant at time t will be equal to 1 on the original concentration of our reactant plus KT. And if I read on, it tells me, you guessed it, what my original concentration was. It was 1.37. And then what it asks us is to calculate the concentration of my reactant 770 seconds later. So it's going to be pretty straightforward, isn't it? It's plug and chug. I'm going to get 1 on the concentration, and then I'm going to just take the inverse of that. So we can do this. So 1 on my concentration at time t, which is going to be my 770 seconds, is 1 on my original concentration, 1.37, plus K, which was 0.00356, times by my time, which was 770 seconds. So 2 sig figs, we should be good. So okay, let's just put that into my calculator. 1 on AT will be, turn it on, 1 on 1.37 plus 0.00356 times 770. There you go. And so there's my 1 on my concentration. So it's 3.471. And that would be 1 on molarity. Now, we don't want 1 on the concentration, do we? We want the concentration itself. So all I have to do at this point to get the inverse of that value is to hit that, x to the minus 1. And we've done that before. So then this to 2 significant figures would be 0.29 molarity. Now, again, the concentration should have been decreasing. So we started at 1.37, and then we went for 770 seconds, and the concentration went down to 0.29. So I'm happy about that. If I got a number that was bigger than my 1.37, I would have been very disturbed, right? The concentration of your reactants can't go up. Let's just check units. Everything was molarity. Yep, molarity in seconds. We haven't made any mistake with our units. No conversions required there. So pretty straightforward, that one. It was kind of plug and chug. All right, just a matter of not making an error. Okay, what's this one? Using the first and second order integrated rate laws. Okay, so I need my table, 12.2 handy. And bring it up there so it's nearby. And I'm going to be, in this case, using the information that's in here. So let's see what we've got. It says, at a certain temperature, the rate of this reaction is second order. I'm just going to say, I knew that anyway because I was looking at the units for the rate constant, and they were molarity to the minus 1, time to the minus 1. So I kind of knew that it was second order. Okay, that's it there. Suppose a vessel contains SO3 at a concentration of 0.45. Calculate the concentration of SO3 in the vessel 0.810 seconds later. Okay, well, this is just the same as what we had before. So 1 on the concentration of the SO3 at times t will be 1 on the original concentration plus KT. They kind of write it in the other order, but whatever. I don't really care. So we're solving for that. So 1 on the concentration at time t is equal to 1 on 0.450, and then my k there was 13.4, and then my t 0.810. 0.810. So 1 on the original concentration plus k times t. There we go. And so 1 on my concentration at t equals 0.810 will be 1 on 0.45 plus 13.4 times 0.81 equals 13.076, right? Now, again, that is 1 on the concentration. We don't want 1 on the concentration. We want the concentration itself. So we have to take the inverse of that number. So we just hit the x to the minus 1 button. There it is. And it ends up being 7.6 times 10 to the minus 2 molar. Now, we started with a concentration of 0.45. 0.45. All right. A fraction of a second passed. It was only 0.81 of a second passed, and the concentration dropped down to 0.076. So we should feel happy. Now I better check the sig figs on this. Yeah, it did say 2 sig figs. So just always go back and double check everything. You know, make sure you're not going to get points for just silly things, right? Okay, that was good. Next one. Deducing a rate law from the change in concentration over time. Okay, so this is where we've got time and concentration. So what we've got to do here, and we notice this reaction has only the one reactant, which means that integrated rate laws are appropriate. So what we're going to do is this. We're going to make 3 plots. We're going to plot the concentration against time. And if we get a linear plot with a negative slope, the slope will be equal to minus the rate constant. Our reaction will be 0 order. We are also going to make a plot of log of the concentration against time. And again, if we get a dead straight line where the slope is equal to minus k, then we know that our reaction is first order. We will also make a plot of 1 on the concentration against time. And if this has a positive slope and is perfectly linear, then our reaction is, you guessed it, second order. So once I've figured out whether it's first order, second order, or 0 order, I can get the rate law, right? Because if it's 0 order, rate equals k times to the concentration of my reactant raised to the power of 0, which is just straight up k. That's for 0. If it is first order, it'll be rate is equal to k multiplied by the concentration of my reactant to the power of 1, which is just, you can just not put the 1 there, and that's for first order. And if it's second order, then my rate law will be Ka to the squared for second order. So what I got to do is I got to make these 3 plots, check if they're linear, and then for the one that is linear, I'm going to look for the slope. Now, fortunately, there's a really easy way of doing this using what we call a stat plot in your calculator, and also using what we call linear regression. So linear regression, what we're going to do here, what we're going to do is we're going to calculate this quantity called r squared. And if that equals 1, then your data is linear. Okay? If r squared equals 1, then your data is linear. Now, the nice thing about linear regression is it also gives you your slope and intercept. And I'll show you how to do this in a moment. So the linear regression will give you the r squared, which will tell you if it's linear or not. And it'll also give you your slope, which we want, and your intercept. So this seems like a frighteningly large amount of work to begin with, but it's not too bad. I'll show you how to set it up now. So the first thing that you want to do is, I'm going to do this in a Texas calculator, and if you don't own one, you can get an emulator, and I've posted to Canvas details about getting one. All right, so that'll make things a little easier for you. So in the Canvas module for this week, there is a video explaining this technique that I'm about to go through, but there's also some data there and some files about how to get an emulator for a Texas calculator, so you can use the exact same procedure that I am right now. And I think the calculator is probably the easiest way of doing this. So fire up your calculator, turn it on. There is sort of like one thing that you should do. You should go into what we call the catalog. So go second function, catalog. And then we want you to go down to D. So find the letter D. There we go. Now it's going to take us down to the Ds. And go to where it says diagnostic on. And you hit enter until it says done. And we need that to be turned on, okay? So the next thing that we're going to do is set up this thing called the stat table. So we're going to go stat, and then we're going to edit, okay? And my one has nothing in there. If there's stuff in there, you have to go up to the heading and clear it off, all right? For each column, you're going to go up to the heading and clear it off, all right? So you just clear them all. Okay, but in this case, there's nothing in there. So now I'm going to put my data in, just like in the table there. 0, 10, 20, 30, and 40. So in L1, which stands for list 1, I've got all of my time data. Then in list 2, I'm going to put my concentration data, and not surprisingly, the concentration goes down, doesn't it? All right. Okay, concentration goes down because my reactant is getting consumed. Now, you'll see in a moment why I'm asking you or suggesting that you use a stat table. What we're going to do now for list 3 is we're going to go up into the heading, and we're just going to enter the formula. So we want the natural logarithm of the concentration. So we're just going to go ln, and then I go second function, list 2, because that's where my concentration data is. And watch the magic, it fills the whole column. Then I'm going to go over to list 4, I'm going to go into the heading, and I'm going to go 1 divided second function, list 2, because I also want 1 on the concentration, and they're all done. So there we go. So in list 1, what I've got are my times. In list 2, I've got my concentrations. In list 3, I have the natural logarithm of the concentration, and in list 4, I have 1 on the concentration. All right, so 1 on second function, list 2, just 1 on the concentration. There we go. So in reality, what my table looks like is like this. This is the log of HI, and this is 1 on the concentration of HI. So now I want to check what ones of these guys are linear, right? So I go into the stat menu, and this time I'm going to do a calculation. All right, so I go over to calc, and the type of calculation I want to do is linear regression. So I can hit number 4 to bring that up. And the first thing I want to check is whether it is 0 order. That is a plot of time and concentration a straight line. Right, that's what I want to check. So I'm going to go time is going to be my X values. That's always going to be my X values. And concentration is in list 2. So then I go down to calculate, and I just hit enter. And you can see that R squared is nowhere near 1. So it is not 0 order. So 0 order is not a possibility. So now I do the same thing and I check whether a plot of log of the concentration against time is linear. So I go stat, calc, number 4. My x's are still time, but now I want my y's to be list 3. And then I go to calculate and I hit enter. And again, it's better, it's more linear, but it's still not 1. So it is not first order. So we kind of know at this point that it's got to be second order, but we're just going to double check. Stat, calc, number 4, list 1, and then 1 on the concentration was list 4. Go down to calculate and hit enter. And then you can see it's not quite 1, but it's like 0.9999999, right? Okay. So now we want some of that data, right? We don't want to leave it right there because what we want is the slope. And in this case, the slope is A. So the slope for this is equal to 0.2843. 0.2843. And so we know that it is second order and we've got the slope there. All right. So now we're ready to go. All right. We're ready to go. So write the rate law for this reaction. The rate, it is second order. So it is K times by the concentration of HI to the power of 2. There you go. It is second order. And then what is the value of K? Remember, 1 on the concentration of HI versus time is linear with a positive slope, and the slope is equal to K, which is why we wrote down the value of the slope. So K is 0.28. Now we have to decide on our units, all right? So we've got to decide on our units. Now, our units are going to be, because this is second order, concentration to the -1, and our concentration unit is molarity, time to the -1, and our time unit is seconds. So both of those. Now, you can look that up in the table if need be. For second order, there it is, right? But just, remembering that K, the units are concentration, whatever your concentration units might be, negative, overall order -1, and then it's always time to the -1. So in our case, our overall order is 2, so 2 minus 1 is 1. So it's going to be concentration to the -1, and then time to the -1. And concentration was molarity, so it's molarity to the -1, and time was seconds, so it's seconds to the -1. So the key thing here is rely on your calculator, all right? And if you don't have a physical graphing calculator, then rely on using an emulator. There are other ways of doing it, and I posted another video with an alternative way of solving this type of problem. I still think that the stat plot and the calculator is the easiest way. All right, here's another way. It says a chemical engineer is studying the rate of this reaction. So this is all about finding half-life and rate constant from a graph of concentration versus time. So here's my graph. Let's have a look here. My starting amount, I've got to read the scale well. So every line is 0.1, 0.1, 0.2, 0.3, 0.4, 0.5. Yep, so my starting amount is 1.2 molar. So 1 half-life would be after when we're at 0.6 molar. So there it is, 0.6 molar. And then another half-life would be when we're at 3. So 0.1, 0.2, 0.3. So it would be there. Now, remember what I said is if the half-life is constant, this is first order. So we go 0 to 1 half-life. The first half-life, T1/2, the first one is 0.04 seconds. And then the second half-life, we go from 0.04 to 0.08. The second half-life is also 0.04 seconds. So T1/2 equals a constant. So what does that tell you? Tells you first order. All right, let me show you why. All right, if you are 0 order, T1/2 will decrease as the concentration decreases. It doesn't, it stays the same. If you are first order, you see that the T1/2 is not dependent on concentration. T1/2 is constant. And if you are second order, you'll see that your half-life increases as your concentration decreases. So the half-life is constant, tells you that it's first order. So that's going to make it real easy to analyze from here. It says, what is the half-life of the reaction? Well, we just did it, didn't we? Round your answer to 2 significant figures. So it's going to be 0.040 because remember, leading zeros never count. Now it says, suppose the rate of the reaction is known to be first order. Well, we already figured that out anyway because we're really clever. Calculate the value of the rate constant. So from my table, it tells me that log 2 on T1/2 equals K. And we know that this is first order. So the units for this are going to be time to the -1. And my time units were seconds. So it's going to be seconds to the -1. So log 2 on T1/2, let's give this a go. I'll bring this over here. And we have to, we have to quit because we're just doing linear regression. Log 2 on T1/2, and T1/2 was 0.04. Booyah. There we go, 17.3, and we've got some information there about sig figs, 2 sig figs, so that would be 17. Okay, all right, cool. And then finally, predict the concentration of the Cl2O5 after 0.2 seconds have passed. So we have the original amount, it was 1.2. So what I'm going to do is there's a couple of ways of thinking about this. One way would be like, 0.2 is like how many half-lives, and you could halve it that many times. But that would be a foolish way of doing it. How I'm going to do it is I'm just going to use the integrated rate law. So the log of the amount at time t will be log of the original amount minus kt, and that's going to be a lot quicker and less prone to kind of messing around. So my original amount was 1.2, so log of 1.2. My k was 17, and my time here is 0.2, right? And that'll give me the log at 0.2 seconds. So the log at 0.2 seconds is going to be, now it's kind of nice we don't have to use the rounded value for the rate constant. So log of 1.2, because that was the original amount, minus, and then I'm just going to bring the answer back before because that's the rate constant, times 0.2. And then there we go, minus 3.283. But that's the log of, that's the log of it. So e to the minus 3.283 will give us what we want. So second function, e, second function, answer, enter. 0.0375. 0.0375, and it's probably molar, isn't it? We'll check that in a moment. 0.0375. So 0.0375, they wanted it is molarity. They want it to 2 sig figs, so it's going to be 0.038 molar. So 0.038 molar. Now, we should think about this. If a half-life is 0.04 seconds, 0.04, how many half-lives have we gone for? Right, we've gone for, well, I know the answer, I'm just being pedantic. Right, well, we've gone for 5 times t1/2. So if you wanted to, you could put in that 1.2 and you could halve it 5 times. 1.2 times, and you could do times a half, 5 times, or you could do times 1 on to the power of 5, right? Because that's the same as multiplying it by a half 5 times. Yeah. And what do we get? Same answer, right? Okay. So it makes sense. We've double checked it every way possible. Okay. So what have you got this week? What you've got is you've got about 4 questions on just using rate laws and method of initial rates. And then you've got about 6 questions concerned with rate laws, but using integrated rate laws and half-lives. Okay, so the big thing that's going to really help you out here is this table that summarizes all of the information about rate laws and integrated rate laws and half-lives and tells you how to do the plots. And the other thing that you really want to have a look at is the example calculations that I have for using the stat plot and linear regression features on your calculator. Now, if you go into Canvas, there's a couple of things here. We've got this scientific calculator emulator, but in the module for this week, in addition to that, I've got these 2 videos here that show you 2 ways of solving integrated rate law problems. One using the calculator, just like what I did, and then another one for those of you that are calculator resistant. Okay, but it's definitely a lot more work. Now, further down here, I've got a couple of problem worksheets, and for each of the worksheets, I've got worked answers where I've done the math basically by hand. Right, so you can see how I go about doing that. So that can sometimes be helpful. These are like relatively simple problems that are kind of good for getting you going. For you guys that love calculus and like integral calculus, I've also provided you with the derivation of the integrated rate laws, which we don't go through in class. I know how to do it. Some of you guys know how to do it, but calculus is not a prerequisite for this class, so we don't derive them. And I understand that sometimes it feels weird if you're just given a formula without being shown where it comes from. So it's definitely a non-trivial amount of work. And yeah, you have to work at it slowly, a couple of topics every day, and you'll get there. And yeah, good luck with everything. Let me know if there's anything I can do to help you.